Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation of topical MCQ on structure and bonding topic 3 in my classification. So this is from question 16 to 20. So in this question is about aluminium chloride. So we associate aluminium chloride as being simple molecular. You will have been able to tell from the law sublimation point. So sublimation is going from solid directly to gas. These are considered quite low. Highs are going to be like 600, 700, 900, anything that seems high, based on the chemistry scale of physical properties, you will know when it's high, all right? So AlCO3 as a solid is most likely going to be like this because it's simple molecular, okay? But then when it goes to gas, when it sublimes, it will dimerize, okay? Dimerize means two of it will come together and give you a structure that looks something like this, where it will not be radical, it will not become ionic all of a sudden, because you start off from simple molecular, you don't become ionic all of a sudden. The question really comes down to which one is correct to represent the dative covalent bond, okay? If you can imagine that the aluminium chloride just looks like your case study for BF3. Oops, I've written down an F there because I was talking about BF3, which is your case study stated in your specification. There is a unhybridized 3p orbital, because the aluminium there is just sp2 hybrid, because, well, you got 3 bond pair and 0 lone pair, all right? So you have 3 electron pair, because 3 plus 0 is equal to 3. You must have the S involved. You must mix in 2, because then 1 plus 2 give you 3. Okay, that's why it's sp2 hybrid. You can watch more of this in my short tutorial video covering specifically on hybridization under the structure and bonding topical playlist. Yeah? The fact that you have these empty orbitals means that when you have two of such molecules, when you have another one of what should I do here? So when I draw these wedges and the bordered line is coming out, pointing right at you in the eye, coming out from the screen, coming out from the paper. This is pointing away from you into the screen, into the paper. This is flat, okay? This is flat in the on the screen or on the paper. So again, this one has empty orbital. So what happened is you can have this chlorine that has a lone pair. In fact, it's got 3 lone pair, and this one here also have 3 lone pair. What happened is this lone pair this chlorine can use one of the lone pair to donate 2 electrons here. At the same time, this one can use 2 electrons to donate to the empty orbital there. So what you're gonna get is, whenever they ask us to draw the dot and cross, I always encourage students to think about the display formula first, all right? Normal, 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 okay? This is normal, this is normal. This is your normal AlCO3. What happened then is, I'm going to use a lone pair to donate to that aluminium. That is a dative covalent bond from the donor to the acceptor. This is a dative covalent bond. Same deal here. This is another dative covalent bond. When you draw the dot and cross, the dative covalent bond electron must both be from the chlorine. Same deal here. The rest is going to be 1 dot, 1 cross, because they are normal covalent bond. All right. So the dative covalent bond is from the chlorine lone pair, not from the aluminium, because the aluminium already has only 1, 2, and 3 electron used up for bonding. It has normal valence electron. So this is actually wrong. You think about which one is your donor and which one is your acceptor, all right? So counting number of electrons. This is another similar kind of concept where they talk about AlCO3 reacting with LiLH4 and that to give you this thing here. So if you draw out this thing, you will realize that the aluminium is going to be 1 hydrogen, 2 hydrogen, 3 hydrogen, and then you will have N, you will have CH3, CH3, and CH3. What you will get, however, if I flip this around a little bit, if I make this the one that goes like that and that becomes a straight line like that, is that you will have a lone pair on the nitrogen, because think about ammonia and think about your ammonia molecule. In reality, I should have drawn three-dimensional for this as well, but I can't be. Okay, maybe I should, because it's actually becoming tetrahedral now, yeah? So it gone from 107 degree when it's trigonal pyramidal, and now it has 1, 2, 3, 4 bond pair and 0 lone pair, because it used the lone pair to dative covalent bond to the empty orbital of aluminium. Same concept as I talked about before. It's got empty orbital. Instead of chlorine, you get the nitrogen that looks like ammonia because it's got 1 lone pair. Fill in the empty orbital. Now you have a change in structure and bonding. This become 109. Previously it would be 120. This one previously would have been 107. Now is 109 degree. Okay. So what do we know? Hydrogen bonding is incorrect because this is a dative covalent bond. I think in some books they will call it coordinate bond, but I personally prefer dative covalent bond really. It's dimeric, this is not Al2Cl6. They're trying to confuse you. Some people, they just know the technical terms without understanding what is going on, yeah? The aluminum atom has an incomplete octet electrons, yes, because it's only got 2, 4, and 6 originally, just like this one, 2, 4, and 6. It's got an empty orbital as a result of incomplete add electron in the outer shell, yeah? So C is the most correct option. Hang on, no, C is not the correct option. It's about this thing, you see, about this thing. So here, the aluminum atom has a complete octet because now it's got 2, 4, 6, 8. Previously, without this dative bond, it would have been incomplete, but now it's complete because it's got 2, 4, 6, and 8 due to this dative covalent bond. And now the bonds are tetrahedrali arranged. It's gone from 120 degree to 109 degree. So very careless mistake there if I hadn't noticed my mistake straight away. But anyway, so don't jump to conclusions straight away, yeah? So this is a popular ion. It's called the cyanide anion. You do more of these in organic chemistry. When you think about HCN molecule, which is one of your case study under your shape of molecule, so that's HCN. Cn minus will look like that. Think about these 2 electrons, and now think about that. HCN is a molecule, it's not ionic, okay? In reality, this is an equilibrium where very little of it exists as the ion. It's a very, 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 very weak acid, okay? That's why the equilibrium favors more to this side rather than this side, right? So it's not exactly ionic in nature, it's actually simple molecular, but I'm just showing you what happened when you break this bond and it becomes H plus with no electrons. The 2 electrons go on the carbon, so you have a lone pair on the carbon. Okay, so typically we would associate the ion not with HCN, but with a proper cation like K plus or Na plus. Then that is fully ionic, alright? So if I convert that into the dot and cross, I will have cross, cross. This is a bit weird now. What do I mean by it's a bit weird? Because I've got the extra 2 electrons there, and I cannot, my carbon only has 4 outer shell electron, right? So it must be dot, dot, nitrogen, dot, dot. Let me think, is that correct? No, that's not correct. Okay, let me start again. Carbon, cross, 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 dot, 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 nitrogen, dot, dot. That is your nitrogen with 5 outer shell electron. Carbon uses 3 out of 4 for forming the triple covalent bond. I have 1 more electron, but I gain an extra electron. That's why I have a charge, okay? I gain an extra electrons. This is the extra electron, that's why I have a charge, alright? So if I don't put a charge, if I use a rectangle, then I will have a total negative charge. That one is the extra electron gain. Cross equal to carbon electron, and dot equal to nitrogen electron. Okay, so I put the charge there because charge is charge, and this is the extra electron there. Bonding pair of electron. Bonding pair of electron. So this is bonding, bonding, and bonding. So there are 3 pairs of bonding electrons. Lone pair on the carbon, there's 1 there because there are 2 electrons now due to the extra electron being gained. Lone pairs on the nitrogen, there's 1 there. Okay, it's a lone pair. Yeah? It's not the number of electrons, it's the lone pair of electrons. Okay. So next is about forming a pi bond. So you know you can get a pi bond from an S and a P. You can get oops, sorry, that is sigma. What am I talking about? I was thinking about sigma totally. Sorry about that. You can get a P and a P like that. Of course, you can also get the other orientation of the P. So if I talk about, I don't know, the 3 different orientation, right? So X, Y, and Z. You can get a sideway overlap like that or like that, all right? So pi bond, so this is a sigma bond because this is a head-on overlap. Okay, this is a correct one because this is a sideway overlap. I was gonna draw this just now, which is the PZ and the S. This is also a side-on overlap. Nope, sorry, this is a head-on overlap. So this will give you sigma, and this will also give you sigma, not a pi. And you don't do this in AS level, but these are actually d orbitals. Okay, these are the d orbitals, and these d orbitals overlap sideway. But because they are the overlapping of the d orbitals, they don't just form the pi bond. They actually form something else called the delta bond. Again, this is not A level. Okay, so the overlap of the sideway overlap of the d orbital does not give you the pi bond, it gives you the delta bond. All right, not that you need to know it in A level. This is the last question of this 5-question series. So it says that the ability of the polymer to prevent the escape of carbon dioxide depends on whether X can form hydrogen bond with the carbon dioxide in the drinks or not. Okay, so how well will you form hydrogen bond with the carbon dioxide? So which one will prevent the loss of carbon dioxide? So if you read the question, it's saying that which one can form hydrogen bond with the carbon dioxide in the drink. So if your polymer can form hydrogen bond with the carbon dioxide, it will prevent the loss of carbon dioxide. And out of all of these, it's got to be OH. Okay, because when you have OH, then you know you can have, I'm just showing part of the polymeric chain. You will have delta minus and delta plus. You have a hydrogen bonded to a highly electronegative element, such as oxygen, nitrogen, or fluorine. And do not forget the second condition. You must have a lone pair. You must have a lone pair on the highly electronegative atom. All right. So hydrogen bond with the carbon dioxide. So I guess carbon dioxide is going to be non-polar actually, but because they are close to the OH functional group there, you can think about the lone pair on the oxygen there being associated with the hydrogen of the polymer, the OH group of the polymer chain, just like that. Okay, so drawing the dipoles, drawing the lone pairs, and labeling that as hydrogen bonding. So that will help you to prevent the loss of carbon dioxide. So I haven't really drawn that well here. It's much clearer in other cases, as you'll see with more examples, I'm sure. Okay, so this is the end of this short 5-question tutorial on the topic 3 structure and bonding MCQ. And I'll see you in the next video. Thank you for watching. Don't forget to subscribe if you haven't, and share the channel with your friends and your classmates. Okay.